Welcome to my class on steady state heat transfer. In this class, we will work out one or two numerical examples involving steady state heat conduction through a composite layer with contact resistance involved. Now let us work out an example problem using this contact resistance. A wall of a furnace is made up of inside layer of silica brick 120 mm thick covered with a layer of magnesite brick 240 mm thick. The temperature at the inside surface of silica brick wall and outside surface of magnesite brick wall are 725 degrees centigrade and 110 degrees centigrade respectively. The contact thermal resistance between the two walls at the interface is 0.0035 degrees centigrade per watt per unit wall area. If thermal conductivities of silica and magnesite bricks are 1.7 watts per meter degree centigrade and 5.8 watts per meter degree centigrade, calculate the rate of heat loss per unit area of wall and the temperature drop at the interface. So you are having two layers. One is silica brick which is 120 mm thick and another one is magnesite brick 240 mm thick. Now the inside surface of the silica brick is 725 degrees centigrade and outside surface of magnesite brick is 110 degrees centigrade. The contact resistance in between is 0.0035 degrees centigrade per watt per unit area of the wall, per unit wall area. So this is for unit area, so much is the resistance. You can say RC is 0.0035 meter square degree centigrade per watt. Instead of specifying it's for unit area, this is a total resistance for unit area. So thermal conductivity of silica brick is 1.7 watts per meter degree centigrade and magnesite brick is 5.8 watts per meter degree centigrade. You have to calculate the rate of heat loss and temperature drop at the interface. So the data given is inside and outside temperatures 725 and 110 degrees centigrade. Thermal conductivity is 1.7 watts per meter degree centigrade and 5.8 watts per meter degree centigrade for these two layers. Contact resistance in between with this layer, there is a contact resistance 0.0035 degree centigrade per wall per unit area of the wall. Or instead of writing this per unit area specifically, you can write the unit as 0.0035 meter square degree centigrade per watt or meter square Kelvin per watt. It's all same. It's a difference in temperature. So it's a degree centigrade or Kelvin you can express. All this you can express in Kelvin also. So the thickness of the layer is 120 mm, it is 0.12 meter, and the second layer it's 240 mm, 0.24 meter. Now heat transfer through the composite wall is T1 minus T3, that overall temperature difference divided by resistance of this layer, contact resistance of this layer and resistance of this layer. So temperature difference is 725 minus 110 divided by resistance of first layer is thickness 0.12 meter divided by area is 1 and K is 1.7. Area is taken as unit because area is not given. For unit area of cross section you should find out. So area is 1, thermal conductivity of first layer is 1.7 watts per meter degree centigrade. Now RC is 0.0035 divided by 1, or you can just substitute 0.0035 because you are taking it for unit area, plus 0.24, that is the thickness of this layer, divided by area is 1 and thermal conductivity is 5.8. that will give the heat transfer. So Q will get as 5326.172 watts. This is the rate at which the heat is flowing through this. And next you have to find out this temperature drop. So generally if you have no contact resistance, there will not be a discontinuity like this. There will not be any sudden temperature drop. So it will not be in same straight line. The temperature, this is the temperature drop in the first layer, and there is a sudden drop in temperature at the interface and then temperature drop in the second layer. The rate at which the temperature is dropping in the second layer and this rate will be different. The slopes are different because the thermal conductivities are different. So slopes will be different, resistance are different, slopes will be different. Now you can express the same heat transfer in terms of this interface temperature. So T1 minus T2 dash divided by resistance, and that is L1 by AK1, and you can get T2 dash from this. So all now heat transfer is known. You can find out T2 dash by rearranging this. T2 dash is equal to T1 minus Q into L1 by AK1. So you can rearrange like this. T1 is 725, Q you already obtained, and into L1 by AK1. Substitute that, we will get the temperature as 349.035 degrees centigrade. You can also write the heat transfer as T2 dash minus T2 double dash divided by the contact resistance. This drop is occurring due to contact resistance. So T2 dash minus T2 double dash divided by contact resistance also will give the same heat transfer. So Q is T2 dash minus T2 double dash divided by RC by A. Rearranging, we will get T2 double dash is equal to T2 dash minus Q into RC by A. So T2 double dash is already T2 dash is known, 349.035 minus Q is known, and RC is 0.0035. So it will work out to 330.393 degrees centigrade. There is a drop of 18.642 degrees centigrade. T2 dash to T2 double dash, from 349.035 degrees centigrade to 330.393 degrees centigrade. Temperature is dropping only at the interface. So temperature drop at the interface is this T2 dash minus T2 double dash. Thank you for watching.